image recognition. Can you name some image-based deep learning model? Model, AlexNet, MobileNet, lot of net you have heard, right? All these are deep learning models, transfer learning based deep learning model for image processing, right? And another very dominant area is natural language processing and deep learning. That's a combination. NLP and deep learning in a combination. Maybe you have heard many model names. Can you name one? Natural language processing and deep learning combination വളരെ popular ആണ്. നമ്മൾ ഇന്ന് കാണുന്ന GPT ഉൾപ്പെടെയുള്ള tools എല്ലാം transformer, maybe you have heard of the term. The session is over or not? Transformer session is over. All of you are participants. What do you understand from transformer? Transformer is what? It's an artificial neural network. It's basically an artificial neural network which is trained to predict the next word from a sequence of words. Similar to so it's basically a neural network architecture, a transformer, which is basically defined or designed for working on text in the machine learning, about image in the machine learning, text in the machine learning, any audio, speech, other than the machine learning, like deep learning. This is a popular domain, but there are different domains on machine learning. This is a different area, graph deep learning. Maybe you might not have heard of this term, because this new area in deep learning has emerged from 2017 a concept, graph structure data, deep learning relevance എന്താണ്, എന്തെല്ലാം ചെയ്യാൻ പറ്റും, അപ്പോൾ അതിനെക്കുറിച്ചിട്ടാണ് ഞാനിവിടെ ഈ സെഷൻ ഹാൻഡിൽ ചെയ്തത്. These are some topics that I will go through. I will move through topics one by one. Before I go to deep learning, I should give a quick introduction on what is a graph. Everyone know what is a graph. What is a graph in computer science? In math, what is a graph? In simple math, simply when we think of graph, what will come into our mind is x-axis, y-axis, a plot, but it's one direction. From the perspective of CS, what is graph? Nodes connected by edges. It's one of the very popular mathematical structure come data structure. From data structure point of view, we think it as a data structure that can hold some data using nodes and edges. From a discrete math perspective, we consider it as again the same thing, nodes connected by edges structure. So there's a mathematical view, there's a CS view. From a CS view, it's more like a data structure. From mathematical view, it's like a mathematical structure. So, what are the applications of this particular modeling? What are the applications of graph modeling? In which all cases you can model data into graph? Even example, you can say graph. When we think graph in terms of real world, we call it as a network. So everyone know, there is no one who has not at least used this term network. Which is the network that is very well known to you? Network, which is the first term that will come to your mind when you hear network, computer network. It was like before 10 years, if I say network, something that comes into your mind is a computer network. Right now, is it a computer network? Of course, computer network is there. In addition to that, when you say think of network, you will think of social network. You will just think of social network. And different websites that support social network like Facebook or LinkedIn or Twitter or many more, YouTube. All these things are social network or social media based applications. And a very simple example is a social network. So when we consider graph as a real world modeling of data, the easiest thing that you can connect is social network. People and their interactions, right? People and their interactions. A simple example of a social network. Then that can be again directed. There is a directed, you know what I mean by directed and undirected. There is not there. If you consider a Facebook as a social network, people connect to people. There in direction, people friend to other people. Is there in direction? There is not a both direction. It is working. Like when you make a friend request to another, you are making a connection between these two. There is no direct and arc. But if you make a follow relationship, you follow one person doesn't mean that that person is following you. So you can model it as a directed graph. So either it can be directed or undirected. So there are many applications for which this kind of modeling is important. The very good example is Facebook. Everyone know what is Facebook. How Facebook grow? How the Facebook grow? What can be your answer? Facebook എങ്ങനെയാണ് വലുതാവുന്നത് means Facebook അവരുടെ സിസ്റ്റം വലുതായി കൊണ്ടിരുന്നത് എങ്ങനെയാണ്? By they will recommend us. You can link, you can connect to this person, you can connect to this person. You can that is a most important thing through which they increase their size, right? They are trying to include maximum person into their network. So if you consider it as a graph, if you consider you and your friends as a graph like this, each node represent you, and this connection represent you are a friend to other person, you are a friend to this person, and Facebook in the back end they can process this as a graph. So whatever we see as in the web page, there is no graph, but internally they are maintaining a graph on the top of which they are doing lot of analytics which applies machine learning and use this graph to provide us recommendations. For example, if this is the current graph, the Facebook can understand that there is a common friend between these two persons. This is connected to this is also connected to this. So this is a common person between these two. And the Facebook can predict this link. There is a possible chance of link between this node and this node. And this thing come to us as recommendations. So the important part of the growing of this social network is how the links are predicted. What are the possible links that can come based on this graph structure? So many kind of this kind of applications. Similarly, recommendations. So this is the case for Facebook. There are different applications through which you can do prediction, you can do recommendation to suggest important products. There are a lot of applications once you model the data as a graph. And social network is one example. Power grid can be modeled as graph. Road can be modeled as graph. Internet itself is a graph, as everyone know. Sensor network can be modeled as graph. And if you cannot directly see a graph, there can be some mechanism you can apply and convert the data into a graph. So modeling data into graph has many advantages. For example, what is a road graph? What is a road graph? If you think road as a graph, what will be the nodes and edges? Road as a graph, what will be the nodes and edges? Two places are the nodes and the road between them is the edge. So in many real world applications we can model as graph. Web itself is a graph. Why web is a graph? Why web is a graph? Web is a collection of pages. There is a hyperlink from one page to another page. So if you consider the complete web, you know it's a web graph. Those who have studied the subject called information retrieval might have studied how this PageRank algorithm works. Have you heard of PageRank? Now PageRank is the first introduced algorithm by Google to rank the pages in the web by considering the web as a graph. With the success of this algorithm, Google started dominating the field of web because the creators of Google first created this algorithm called PageRank, which considered the web as a graph, and that algorithm ranked the pages based on its relevance. Then from biological field it is there protein interactions. Proteins തമ്മിലുള്ള interaction. It can be modeled as graph, gene regulatory, gene interactions. So almost every domain has a scope of working with graph. That's why I am giving us introduction. And there are a lot of things you can work on the top of the graph. You can apply machine learning and can explore the interactions. What can be the next possible interactions? If there is some change, you make some delete some nodes, how the graph can be restructured. And if you model the data into a graph, can be trained to an algorithm and can be used to predict the outcome. If you give a sample graph, all these things are possible. So you can see the diagram as a gene graph, gene interactions, cell graphs. Now, sometimes maybe the graphs are not naturally given. Even you can generate a graph from this data. What is this? These are images of different films. How can you construct a graph from this? Think of it. There are these films are different films. How can you construct a graph out of this? You compute the similarity between two images, and if they are found to be similar beyond a threshold, they can be connected using links. Similarity. There are some common data. All these films have some common data. So based on that, if you found the similarity, if you found a similarity between two films, same director, same actors, same language, you can give some link, and you can convert it into a graph like this. So even if you cannot directly find a graph from the data, even if in that case also you can construct it from the given data. And I will do some very popular task. Once you make the graph structure, what are some very popular tasks? One thing is community detection. The diagram can tell you what is a community detection. So in the graph, so this is a co-author. What can be a co-author network? Anyone might have read some research papers, right? A co-author graph or a co-author network. What can be co-author? Many of us have published many research papers. If two of us has together come in one paper, I can say there can be a link between me and this person. That's called a co-author. There can be many papers, many authors for a single paper. And if one paper is co-authored by two people, there can be link between that two people, and that is called this co-author network. So this network means that every node is an author, and there is a link between the authors if they co-author at least one paper. Clear? And from the co-author network, each author has different areas. And once you apply some community detection means finding some dense areas in this network. If we can find which are some dense areas in this network, dense means highly connected. If you plot it, it can be like this. From this we can make the inference that these set of authors, these authors are highly connected, and we can observe that they may be working in machine learning area. These authors are highly connected, which may infer you that they work in information retrieval, and these are some authors who are highly connected, they are working in data mining. So to making this inference, you can apply community detection. Community detection is nothing but finding dense areas in this network. And another kind of task called a node classification. I think everyone know what is the meaning of classification in machine learning. You can look into that graph and understand what is the meaning. So D1, it is marked as democratic. D2 is marked as Republican. based on the graph structure, I can say D3 and D4. So we assume that the people having different tastes are connected with each other. So what can be the inference? What can be inference to this D4? The inference to D4 is Democratic or Republican? It is as D2 is Republican, there is high chance that D4 can be Republican itself, because there are two people. This person can be reached to this person within 2 hops of person. That means there is high chance that the person. Similarly for D3 also, D3 can be the same class as that of D1. So if we have a graph and if we know the levels of some nodes, so this is the level of D2 is Republican and the level of D1 is Democratic. And if we model the data as a graph, and if you know the levels of some nodes, using some mechanism, using graph classification algorithms, you can predict what can be the levels of another nodes. And this task is called network classification, or simply node classification. Even face recognition is a very well-known task. Even you can use face recognition, convert face recognition as a graph-based problem. So, in looking into the diagram, we'll tell you what is the meaning of this diagram. We have several images and we have converted it into a graph. See, what is the meaning of edge there? What is the meaning of edge in this graph? Edge and the weights are given to edge 0.7, 0.4, 0.9. What does it mean? Faces which are similar. So faces which are similar. So you can use a simple similarity comparison between these two faces and give an edge if they are found to be similar. Again, you can see this face and this face. Similarity is found to be high, so I have put the edge here and give the weight as 0.7. But when it comes to here, the similarity between these two is different, and these are different persons. So, suppose we know only this person's name as Brano, and don't know if we give a new input of his smile face. Once we model it as a graph, from this graph I can infer that this person is also Brano, or this person is also, this figure is also Brano, that one is Brano, and if we give input as this person, I can say it is not Brano. It can be according to that. So based on this connectivity, you can make predictions, and that's what semi-supervised. There is not complete level information is not available here. Part of the level information is available, using which you can predict the level of others, and such task is called a semi-supervised learning. So as I told you, these are some of the very most commonly used tasks: node classification, link prediction, community detection, network similarity, ranking, etc. Now, so as I already told you what is a network, what are different applications that you can build on the top of network. Now, we will look into how you do machine learning on this graph. How will you come up with an algorithm for link prediction? How will you come up with an algorithm for node classification? For that, you have to apply machine learning. But traditional machine learning will not work properly here. What is the way of traditional machine learning? So that's why I asked you whether you have gone through the concept of machine learning. What is the traditional way of doing machine learning? Someone say, some student can say, to do machine learning, what we need? You need a data set. You need a data set. How the data set look like? If it is images, you have plenty of images. That's it. But for structured data, image you have to convert them as features. Right? Images convert. And what are the features of image? Image features are what? Pixels. right? Pixels. So you can consider an image as a grid structure, like a grid structure with each smallest unit represent a pixel. Fine. And is there any connection between pixels? If the pixels are somewhere connected, no, each is an independent pixel. Right? But there is an ordering for the pixels. There is an ordering. Pixels are ordering. And leave this image classification. Think of simple data set, simple data set. So what are each row represent? Like which classification program that you are? Iris classification. Is it familiar? Iris classification problem? So no. Machine learning you have not got in the lab. Okay. So usually we have a data set, means it has a lot of features. And there are many rows. Each row represents a sample. And there can be n features. And once we have the feature, we vectorize the pass to a classification algorithm to classification. But when it comes to graph, this traditional way of feature construction will not work, because traditional machine learning algorithms assume that the features are independent and identically distributed. But when it comes to graph structured data, this assumption doesn't work, because they are not independent. People are connected with each other and they are not generated from the same distribution. So traditional machine learning algorithms you cannot directly apply on graph. You need to convert the graph into a particular feature representation. Then only you can apply traditional graph algorithm. So this particular area of how to convert the graph or the network data to a low-dimensional representation or a vector. So machine learning, when we say machine learning, we think of how the data is converted into vectors. On the top of vectors, you are applying algorithms. If you be linear regression or logistic regression, all these things are built on the top of vectors. So converting them to the vectors is very important, from data to vector. So this area called network representation learning or simply network embedding is how we convert from graph to vectors. Let me move again to some basics of how we store graph in computer memory. Everyone can answer. How you store a graph in computer's memory? From a data structure perspective, what is the answer? How a graph stored in computer memory? As an adjacency matrix, right? As an adjacency matrix or an adjacency list. Usually we think of array or lineage. So same thing represented here also. My task is to do machine learning on this graph. To do machine learning, I have to convert every node into vectors. So for timely, you just understand this thing. To do machine learning, this graph structure should be encoded in a vector format. For that, this every node should be converted into vectors. Now, the first thing that comes into mind is think of an adjacency matrix. So this is an adjacency matrix. See what each row represents. Each row represents. So here, information will be not 0, 1. Degree values will be whole 3, 2, etc. is showing. So what each row represents? Each row represents whether that node is connected to other node. Whether that node is connected to other node. So this one means that this is not 10 is connected to which node? 1. 10 is not 10. Suppose there are 10 nodes. Node 10 is connected to first node. Whether it is connected to second node. Whether it is connected to third node. So if the size of this graph is n, what is the size of this matrix? If the size of this graph is n, size of the graph means the number of nodes in the graph. What will be the size of this matrix? It will be n by n matrix. And you can think like each row represents. So this is for node 1, node 2, node 3, node 4, up to node n. So see, think of this row, last row matter. That last row you can consider as a vector. Like each row you can think like a vector. each row you can think as a vector because we have converted into numeric. So this graph to this adjacency metric representation itself is a way to convert from graph to vector. You need to apply machine learning means you need to get vector from a vector corresponding to every node. So each row you can consider as a vector here. But the problem is, in real applications, what is the problem is there will not be many connections. As a result, there will be data sparsity in many of the entries will be zeros. Similarly, when the graph is very large, these metrics become very large and the dimensionality will be very high. So in machine learning, there is a fundamental concept called curves of dimensionality. When the dimensionality is very high, what is the problem? The time taken to learn the model will also be increase high. So it is very important to reduce the data size or the dimensionality of the data before passing to a machine learning algorithm. So you cannot directly input these metrics as such to a machine learning algorithm because of these kind of problems. There are sparsity issues, there are dimensionality issues, and also it doesn't represent the semantics. A semantic example that I can tell you is, see, these three nodes are connected to this node. So this person is a common friend. This person is a common friend of these four. And you can observe that this person is connected to this four. That information is represented in this matrix. So no. You cannot directly infer that thing from this matrix. But in the graph, if you look into the graph, you can easily understand that thing. There are many semantics inside the graph. All these things you cannot encode as a adjacency matrix. Even if adjacency matrix can be represented as n rows, each row represents a vector, you cannot directly use it for machine learning. Now I can give you a more formal mathematical, I don't know how many of you are interested in mathematical definitions, examples, explanations, etc. I can give you a much more mathematical definition of what is a network embedding. Embedding, I think you have heard of it. In many places you might have heard this term embedding. What is embedding? If you are a person who is interested in machine learning, data science, you have this word, embedding. What is embedding? Embedding is nothing but representing the data in vector space. That is the embedding. Nothing else. Convert it into a lower dimension. Usually called that as a latent space. In machine learning, this is a very common term called a latent space. If we have an original data which is called, we are considered as a feature vector, but if you reduce the dimension and get into a lower vector or a lower dimensional space, we call it as a latent space. So embeddings always happen in this latent space. So the task of network embedding, this is the original graph. This is a little not popular graph called a character graph, which shows people the interaction between different people in the network. And this thing, you convert this graph into a vector space. You can see this is a two-dimensional space. So each point represents, here you can see every node in the graph has become a point in this space. Every node in this graph has become a point in this space. This process of converting from graph to this vector space, here it is represented in the two-dimension. Converting from graph dimension or graph space to this vector space is called, we call it as network representation learning. And if you observe these two diagrams, what you can infer from these two diagrams? Someone can tell what you can infer from this diagram. These two diagrams, look at this diagram. What do you infer? What? On the graph, on the vector space. tell? From both these diagrams, what you will understand? Colors ഒക്കെ നോക്കിയാൽ മതി. Colors. You look at the colors and you will get it. Colors will tell you what is the meaning. Yes, correct. Oh no. See. Same colors. See. Think it like a set of people here. Think this as a set of people which is represented in this color, and almost they are connected to each other, or they have some common friends, or somewhere they form a sub-network here, right? They are found to be clustered here. Here also you observe these people are closely connected to each other. They are highly related to each other. These people are some highly related to each other. Similarly, this code also. And if when we convert this into vectors, what happened here also, or what should happen here also? Same property should be preserved, which means people who are close in this graph should be close in the vector space also. Here you can see two colors are purple colors are origin. You can see these colors are coming together. Again, these colors are coming together, which means people who are very close in this graph are found to be close in this vector space also. People who are highly connected in this area, again they are found to be very close in the graph space, in the vector space also. And this is how we want to convert. So, ഇങ്ങനെ convert ചെയ്യുന്നതിനാണ് ഈ property preserve ചെയ്തുകൊണ്ട്. So we need to convert the graph into vectors so that these proximities are preserved. And the proximity can be first order, second order, higher order. So you can simply think like what can be a first order proximity? I am closer to this person. He is closer to next person. There is a proximity between he and that third person, right? So a friend of friend. You can think in terms of a friend of friend. A friend of friend. First order. A second order means friend of friend of friend. So in this example, even if these two people are not connected, there is no direct connection between these two. Friend of friend relation exists. Similarly, friend of friend exists between these two people. So all this information, these people, there is high chance that these people are doing something very together. They have some similar taste. They belong to some same category. That is why they are highly connected. This information should be preserved while we convert from that graph into vectors. And such converting from graph to these vectors by preserving this property is called network embedding or graph representation learning. Why? The importance is that on the top of this data we are further going to apply machine learning. You can apply any machine learning algorithm once you convert graph into vectors. For example, a new person comes and suppose he will come here. His vector, that new person's corresponding vector will come here. What can be an inference? You can think in which group he may belongs to. He may belongs to this group because he is connected to, he is very near to all this group. What that algorithm in machine learning called? In machine learning, that simplest algorithm, you find the distance of a point to the nearest point, assign that person to that class. It's called to classify a point, compute the distance of that point to the nearest 3 points, assign the point to the class of that majority of that points. We Which algorithm? Point, you need to classify one point. Find the nearest 3 neighbors of that point. Assign the point to that class. KNN classifier, right? KNN classifier. Maybe you heard of it, right? Yes or no? Yes or no? Yes. A K nearest neighbor classifier. So once you convert this input to this particular representation, you can apply classification algorithms like that KNN classifier, or you can apply clustering. You know, you have heard of clustering, right? What is example clustering algorithm? K-means clustering algorithm. You apply K-means clustering algorithm, you can identify that this is going to be a cluster. So even if you don't know how to apply a graph clustering algorithm, once you convert it into this feature representation, you can apply a K-means clustering. Graph clustering, there are different algorithms for graph clustering, but if you want to do it as a machine learning perspective, you can convert this graph into this vector space and apply K-means clustering, find the clusters from this graph. So traditional machine learning you can do with graph data also. To do that, you need to convert graph into vectors. So here, for easy visualization, it is represented as 2-dimensional, as a 2-dimension. So as I already told you, all these things. So the important thing is when you convert from this graph to vectors, it should preserve the structural property of this network. Structural property, the nodes which are connected to each other here should come closer in the vector space also, and that is called the structural property. So that preserve the structural property preserve these two nodes are connected. And when it comes to graph, one come here and one come here, means the conversion that you have done is wrong. So network representation learning is the area of how to convert from this graph to vectors. What are the different algorithms that we can use to convert from graph to vector representation? It's a very, very big area. There are different mechanisms for that. I will quickly introduce one or two. So network embedding can be considered as a structure preserving dimensionality reduction. I think you might have heard of this term dimensionality reduction. So no. Can you give some name? So in this session we assume that you have already studied machine learning, you studied deep learning. From where we start this software. So can someone tell what is dimensionality reduction in machine learning? Any idea? Dimensionality reduction? Using very simple method, very common method called principal component analysis. Right? Heard of it? So no. Yes. So basically we are reducing the dimension by preserving the structure. Now I will conclude up to from the point where we started discussion. So we have the network. We have to convert this network into vectors. So here you can see we have different nodes. We convert the nodes into vectors. So once we have the node representations or node vectors, there is no link between these vectors. But that link information is encoded here. That is the most important thing you should understand. Once you convert the graph into vector, there is no further link. Every node has become a vector. There is no further node, there is no graph. But the link information is encoded in the vector. Encoded means if there is a connection, or if in the network space, if these nodes are close to each other, even if they are connected, or even if they are close to each other, what will we observe in this graph, this vector space? What will be if we observe in the network space? If the nodes are connected in the graph space, in the corresponding vector space, those two vectors are closer. Are you getting the point? Is it clear? അതായത് ഗ്രാഫിൽ നോട്ട്സ് അടുത്തടുത്തുള്ള നോട്ട്സ് ഏതൊക്കെയാണോ ആ നോട്ട്സിന്റെ കറസ്പോണ്ടിങ് വെക്ടേഴ്സ് എടുത്ത് നോക്കുകയാണെങ്കിൽ ആ വെക്ടേഴ്സിന് എന്ത് തന്നെയായിരിക്കണം? അടുത്ത് തന്നെ ആയിരിക്കണം. How you compute the similarity between vectors? That everyone can do. So once you convert the graph into vectors, the important thing that you should preserve is those nodes which are closer in the graph space, which means they are connected. These nodes are connected, or there is a one hop path between those, or there is a two hop path between those nodes. They are very close to each other in the graph. Once we convert them into vectors, then corresponding vectors also should be close to each other. How you find or how you compute the similarity between two vectors? Check whether they are close to each other. What are the different measures to compute the similarity between two vectors? Somebody tell how to compute similarity between two vectors. All of you are CS, right? Tell how to compute similarity between two vectors. Students, you came in the first year or two or not? It is there from 9th standard. My son is studying from vectors, similarity between two vectors study. Someone tell how to compute the similarity between vectors. Two vectors, 0.23, 0.53. How do you compute the similarity between these two? Similarity is proportional to distance. The distance is high, similarity is low. How do you compute? Euclidean. Why you are not getting it? Euclidean distance, right? Euclidean distance. The Euclidean distance is x1, y1, x2, y2. Euclidean distance is square root of x1 minus x2 plus y1 minus y2 the whole square, right? Euclidean distance. One measure. Euclidean distance is high, means similarity is low. Another measure is cos theta. Cos theta. Cos theta between vector A and vector B is A dot B by length of A into length of B. If the cos theta is high, means high similarity. If cos theta is low, means low similarity. The theta is the angle between the vectors. Cos theta is the reverse case. So if you find cos theta, according to cos theta, I can measure the similarity. Higher the value of cos theta, higher similarity. Or angle recording, higher the angle, lesser the similarity. Cos theta, higher the cos theta, lesser higher the similarity. So we can use different similarity measures. And now I will quickly introduce to some well-known methods of how we convert graph to vector concept. What is the algorithm used? How can you convert from graph to vectors? This is the next thing that we will discuss. So, let me try to explain in simple terms what are the most simplest method. So this is a graph. Two vertex U and V. I need to encode U, I need to encode V and convert those two vectors ZU and ZV. ZU represent vector. Think in terms of 2-dimensional, 3-dimensional, any dimension. I need to convert that U to a vector, V to a vector. Let them as ZV and ZU. The simplest thing that I can think of is if there is a link between these two. If there is a link between U and V, what should be this distance? If there is a link between U and V, the distance between vectors ZU and ZV should be minimum. Distance should be minimum. Similarity should be high. Correct. Similarity should be very high. That means the distance between these two ZU and ZV should be minimum. So that is represented as the goal. Our goal is to define a similarity between using the vectors of ZB, ZU and ZB. Take the dot product. Dot product is also always used to find the similarity between two vectors. If, as I told you, dot product is nothing but the cos theta between the vectors. So if the dot product between two vectors is high, the similarity will be high. So my objective is to find ZU and ZB such that if the points are connected in the graph, their vectors are similar or vectors are close to each other. Now, I will tell the matrix factorization algorithm, which is an optimization algorithm. Do you have some idea about what is an optimization? Like what is the loss function of linear regression? All those things you know or not? So no. Loss function, how to optimize it using gradient descent. So all these are fundamentals in machine learning. How a linear regression algorithm works, how a logistic regression algorithm works. So see, this is similar to that. You want to optimize ZU and ZB such that if there is a link between U and V, the corresponding vectors are also closer to each other. To find such ZU and ZB, I should define a loss function. In machine learning, you will get the term on a loss function. Can you name some loss function, a very popular loss function in machine learning? Very popular loss function. Also studied deep learning, machine learning, done some programs. Mean square error loss, right? Mean square error loss. Similarly, cross entropy loss, binary cross entropy loss. There are many more functions. So, if I task, I need to define a loss function. And the task is you need to convert the complete nodes in the vertex space V into V into ZU and ZB such that the difference between ZU, the dot product of ZU and ZB and the adjacency information, A is the adjacency matrix, and that is the loss. This loss should be minimized. It is a bit difficult to understand math if you are not into it. But what I can conclude from this, if this U and V are connected, think in this perspective. Suppose take any two nodes, U and V. If they are connected, what is the value of A corresponding to that U and V in the adjacency matrix? U, V, രണ്ട് vertices connected ആണെങ്കിൽ adjacency matrix ൽ അതിന്റെ corresponding value എന്തായിരിക്കും? 1 ആയിരിക്കും. അല്ലേ? 1 ആയിരിക്കും. അപ്പോൾ if they are connected in the vector space, if you take the dot product, what do you like to get? What do you expect to get? Take the dot product of ZU and ZB. It should be, dot product should be 1 because they are highly similar. If they are highly similar, dot product should come as maximum. The dot product should become as maximum. That means if the dot product between these two vectors are 1 and the corresponding entry in the adjacency matrix is also 1, the loss is, now what is the loss? 0. The loss is 0. So that is the ideal thing that we want to achieve. Suppose, now I will tell the other case. If the adjacency information is 1, if the adjacency information is 1 and the dot product of vectors will give you 0.3 only, then what is the meaning of that? That encoding is not correct. That encoding that you have done is not correct. And that is, in that case you have loss. What is the loss? 0.3 minus 1, 0.7. And if you take the positives only, 0.7 loss is there. That is, in the vector space they are not close. The similarity is very low, 0.3 only. But in the adjacency matrix, if looking into that, there is one, there is a connection. So the encoding you have taken is not correct. So the loss is very high. So If ZU and ZK are very close and the adjacency is 1, there is no error. In other case, if similarly the other case